And pull up the chat. Okay, cool. All right, so we're finally starting chapter 2, which is technically finally into calculus. So this is a calculus course, and we're just getting around to talking about calculus. So if you've seen calculus before in your life, we are going to kind of build up to the idea of something called the derivative. So if you kind of already know calculus, we're going to take kind of a roundabout way of getting there, but we are going to get there. And if you haven't seen calculus before in your life, then it's fine. So the first thing we're going to talk about is, other thing before we get there. So just a reminder, I think I said this last time. I tried to remember to say it, but if I didn't, remember you don't have anything due tonight. There was no homework assigned last week because of the exam. So your homework has, for this week, appeared today. It covers 2.1 through 2.3, which we should cover by Thursday. So we'll finally kind of be on track for that idea of everything that's on the homework gets covered by Thursday, so that you kind of have the entire weekend to work over all of it if you wish. We were kind of behind beforehand, but hopefully now we can get back to the format I kind of like to be in. Anyway, so that's up. We'll be up. We should get through all of 2.1 and hopefully start 2.2 today, and then we'll finish 2.2 and do 2.3 on Thursday. So 2.1 is about this idea called the instantaneous rate of change. So what that is, so first thing is that we need to recall something from chapter 1, so what we just went through. So remember that the average rate of change between x equals a and x equals b on a function, we find that by doing our f of b minus f of a all over b minus a. One second. And that's essentially the idea we're going to build upon now, is we're going to take this idea of this average rate of change and we're kind of going to build up. So say we have this table and it's showing us we're going to throw a grapefruit straight up into the air and we're going to record the height that it's at for certain times. And first thing we're asked to do is find the average velocity between t equals 0 and t equals 1, and then t equals 1 and t equals 2. So that is something we already know how to do. That's still this idea from chapter 1. So if we want to find the average velocity, well, remember that's just the same thing as average rate of change. Excuse me. So we want the average rate of change between 0 and 1. So we essentially end up with 90 minus 6 over 1 minus 0, which would result in a velocity of 84 over 1. So feet per second. And then if we want the average velocity between t equals 1 and t equals 2, we have 142 minus 90. Can't see my screen. Sorry. Reshare. See it now, Merrick? Hooray. Okay. So what am I doing? Average velocity. Average velocity between 1 and 2 would be our 142 minus 90 over 2 minus 1, which would give us 52 over 1, so 52 feet per second. So again, at this point in time, we haven't done anything new yet. This kind of part 2 is where we start getting into this new idea. So we've just found 2 average velocities, but say I actually wanted to ask you, what is the exact velocity at t equals 1? Now, we can't really find that exactly right now because we don't have a velocity function. All we have is 0, 1, and 2. So how would we possibly be able to estimate it? Well, if I look at these average rates of change, these average velocities that I just found, if it's going on an average velocity of 84 feet per second between 0 and 1, and then an average velocity of 52 feet per second from 1 to 2, the actual velocity at exactly t equals 1 must be somewhere between those two values. I don't really know where, but somewhere between the two. So there's going to be a couple ways that we're going to be able to estimate this idea of the exact velocity at a single point. So what we could do, we kind of have two choices, and we're kind of going to build on these two choices as we go through these notes. So the first thing we could do is we could average the two average velocities. So if we were to average these two values now, and there's unfortunately a lot of the word average floating around in different contexts. So I'm taking these average velocities and just kind of taking the normal average of them. So I'm adding them together and dividing by 2. I forget what this is. I think it's like 62, 64, 68. I really don't know what makes this zoom in so randomly. I have yet to decipher what I do that makes it do that. And there it goes again. Oh. So if I kind of average those two average velocities, ooh, the lag on that screen is immense. There it is. Okay, so if I could average those two values that we found in part 1, and that would probably get me a better estimation. So I could say probably around 68 feet per second is where it might be, the velocity might be around t equals 1. The other thing that we're going to be able to do as well is if we had values closer to 1, so if we had values closer to 1, that would provide a better estimate. So say we actually knew like the value at time equals 0.999. I forgot to write down the value for that. Let's just make something up like, wait a minute. I got this. 89.932. I had a value that I wanted to use for that and I forgot to write it down. So let's say that we actually had more data here and we were actually able to record the height that it was at time 0.999. If we were to find the average velocity there, we'd have 90 minus 89.932 over 1 minus 0.999. And let me just triple check that this comes out to what I wanted it to be. Yeah, this would come out to 68 once it catches up with me. There we go. What's up, Sean?
So I understand that for t, when t equals 1, like do we have to use like the surrounding values around 1, like for 0 and 1 and then 1 and 2, or could we use like 2 and 3 or 3 and 4, or would it have to be surrounding like what t equals for like problem 2?
Yes, so I'm using this one as kind of a build it up example and not quite a do it out fully example. But what we would use is, since we want to talk about t equals 1, we would want to look at the values around 1. So that's why we're using 0 and 2, because those are the values kind of encasing it, if you will. We wouldn't want to use any of these values back here because they're essentially too far away from the number we actually care about. So we are going to want to use the numbers that are nearby the value that we're actually trying to care about, which is exactly what you were saying, yeah. So notice I specifically made it so that the 68s matched up. That wouldn't necessarily be the Sometimes we might be able to average these two values and we wouldn't necessarily get the exact same answer as if we had extra data. Sometimes we won't be able to find extra data. So it kind of depends on the problem. And again, we're going to see some more examples in a second that do kind of one or the other and not both. So this is kind of just presenting us with the idea of what we're going to be doing, and now let's get around to seeing how it's actually going to work. The 0.999 and the 89.932 I pulled out of the air. They would be given to you. You would not be finding them. They would be given to you. And I just kind of spoke them into existence. So again, so this is kind of, I'm just trying to set us up here. Set us up. And we'll see some actual full calculating examples in a second. So in a general calculus course, now I know that this is technically a calculus course, but we don't cover as much as, say, Calculus 1 would. So there's this notion that I have to talk about because it's used in these two definitions below, but we don't actually talk about it in full in this class, but I still have to tell you kind of what it means so that you can understand the definition. So there's a notion of this thing called a limit. And what a limit does is a limit approximates the behavior of a function near a certain point. Usually that's going to be looking at y values when we approach certain x values, but it can also just essentially mean that we're letting something get close to something else. So I'm going to babble about that a little bit, and then we'll define these two things that we kind of need that definition for. So kind of zoom in on the side over here. Now note, again, we don't study this in full in this class. So I'm presenting this idea so that I can define these things. So you should understand the spirit of them, if you will, but you don't need to like completely 100% necessarily get the like how you would find them. Because again, we don't study them in full. I just need to kind of talk about what they do so that the definitions will make sense. Say I had some weird function that looks like this, and this was x equals 2, this was 1, and this is 4. Now again, because I need to just talk about the spirit of it, but I don't want you to like learn it, I'm going to write down some notation. Don't forget about the notation. I could talk about a limit as x approaches 2. So what I essentially would be doing is I'd be looking at what the function is doing as I approach x equals 2. And we have this notation for limits where I can also come from the right or the left. So if I put a little minus sign behind it, it means I'm coming from the left. What this would be doing is this would be saying if I'm coming from the left of the function, as I move along the function, as I get closer and closer to x equals 2, where do I end up on the function? And as I come from the left side, I end up at that kind of top point at y equals 4. So like the limit here would technically be equal to 4. And then if I wanted to say, well, what about the limit from the right? Well, that would be saying follow the function as I come from the right side, and as I come from the right side, I kind of end up down here. Now, even though that dot isn't filled in, so technically the function isn't defined there, the limit is just asking what happens when I get obnoxiously close to it. So as I approach x equals 2 from the right, I would be at a height of 1. Now again, that's the spirit of a limit. So what you should take away from a limit here is it's this idea of getting really close to something but not actually ever getting there. You know when you're like 5 years old and you go up to someone and you like put your finger really, really close to their arm and you go, I'm not touching you, I'm not touching you. That's essentially the idea of a limit. Is you're getting obnoxiously close to something but never actually quite getting there. And then you essentially calculate where you are, if you will, as you're as close to that thing as possible. So like when I calculate these limits in general, I never actually reach 2, I just get obnoxiously close to 2 and then kind of see where the function's at. So that's the idea that you need to kind of have in your back pocket for these next 2 definitions, is that we're essentially going to be taking something and making it obnoxiously close to something else. Okay. So that was like the briefest little overview of what a limit is. If that freaked you out, you can probably just forget about it. But we needed to define limit to be able to talk about these next 2 definitions because they use the word limit in it. Did someone else just raise their hand? I have 2 raised hands now. What is up, Jack?
Is the limit the same thing as an asymptote?
No. So an asymptote is a line. No. It depends on what type of asymptote you're talking about. So limits are often referred to when you're talking about asymptotes. So they often kind of come together, even though limits are used in much larger context than just asymptotes. But asymptotes are essentially kind of imaginary lines that tell you what a function is doing, like what it's how it's behaving as it's approaching a certain number. So yes, it kind of has this notion of a limit where, like, if you approach an asymptote, you might start going upwards forever. So you'd say the limit goes to infinity, but technically they're different entities, and limits are used in much larger context than asymptotes are. But they do kind of go hand in hand. So these definitions that we want down here. So why can this go away? I need it to go away. It's not going away. Anyway, I'll be okay. The instantaneous rate of the instantaneous velocity. Instantaneous velocity. Okay, so that screen's doing fine. That screen is lagging for 5 million years. Why is that one so laggy? Let me try to fix that. I have this up on 3 screens as opposed to 2 usually, and the one is lagging. But if it's lagging for anybody else, then I want to make sure that I, don't go too fast. Oh, and now I can't see anything. No, there it is. Okay, maybe that'll help. Anyway, I'm babbling to myself. I'm sorry. The instantaneous velocity of an object at time t is defined to be the limit, which is why we kind of needed to talk about it, of the average velocity of the object over shorter and shorter time intervals containing t. Now I'm going to draw a diagram in a couple seconds that will hopefully demonstrate what I mean by that. Now, just like with average velocity, so average velocity was a very specific case of average rate of change, right? So it was like specifically in the context of distance functions, but like it was the exact same thing as saying average rate of change. Same kind of idea here. We have an instantaneous velocity. We also have an instantaneous rate of change. Okay, let me rewrite that better. Instantaneous rate of change. So the instantaneous rate of change of f at a, which is also sometimes just called the rate of change. So they sometimes drop the word instantaneous and just say rate of change, is defined to be the limit of the average rates of change over shorter and shorter intervals containing around a. So what did that have to do with what I was saying about a limit? So let me write down a couple more things, then I'm going to draw my picture. So essentially, we want to find the average rate of change I'm going to abbreviate rate of change, if you will. For as small an interval as possible. Sometimes we're going to be able to make it really small, and sometimes we have to make it just as small as we can. Now I'm going to write down the kind of official definition because it might help somebody. But if it freaks you out, forget about it. Just go with these kind of less formal definitions down here. So leaving a space on purpose. And if you ever want to freak your friends out with math notation at parties, just pull out this. Anyway, so if I write this down, this might look super freaky, but it's just a slope. You know, we have f of x plus h and the x plus h, and then f of x and just the x. So this is just a slope. It's just written very generically. So essentially what the instantaneous velocity is doing is it's taking this kind of idea of these average rates of change, these slopes, and it's taking the limit as h approaches 0, because what that's going to do is that's going to make this point obnoxiously close to f of x. Because if h is really, really close to 0, then f of x plus h is really, really close to f of x. Like I'm essentially making these 2 points obnoxiously close to each other. So that's kind of what it means by the limit of these average rates of change over shorter and shorter intervals. We're essentially forcing these 2 points in the average rate of change to being as close as possible. So let me draw my picture to kind of also say that as well. I'll leave this up for like 5 more seconds if someone's trying to write it down. Drink some water. So if I wanted to draw this kind of in a picture, I'm going to skip down a little bit down here. Now, because I wasn't thinking about doing this first, brought it down here. This is the same thing as the instantaneous rate of change. Instantaneous, whoops, rate of change. Okay, and now I have to draw this very nicely. Let's see. 1, 2, 3. And I want to do, that'll do, I think. So say I have some function, and say I wanted to talk about the instantaneous rate of change at x equals 2. What that's going to actually end up being is it's still going to end up being a slope, just like the average rate of change is. The slope it's going to end up being, though, is the slope of this line, and I'll talk more about this line in just a second. So the instantaneous rate of change at x equals 2 is going to end up being the slope of this line, this one right here. Now, this line is a very special type of line, which let me define kind of right below it. And well, let me pause for a second for people to catch up because I know I had to draw a function and then I had to draw a line and blah, 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 blah. So we have this line. Now, it's a special type of line called a tangent line. So a tangent line is a line that intersects a function at a single point, but I also kind of need to say in a small interval. And I'll explain that in a second. So if I can draw another function over here really quick, then I'm going to erase in a second. Now I'm going to be saying tangent line a lot, so this is why I want to formally define it, even though it's technically formally defined in your book until 2.3. But anyway, so say I was talking about a tangent line of this function now for just a second. And say this was x equals 3. This line, this orange line that I just drew, only intersects the function at x equals 3, kind of in that small interval. Yes, it does kind of come and touch the function back here as well. But the point of a tangent line is more that what we're saying, when we're saying it only intersects once, we kind of mean in that kind of interval that we care about. So this would be the tangent line at x equals 3. So it only intersects the function at x equals 3, and then maybe somewhere far off later it intersects as well, but kind of in a small interval around the point that it actually is the tangent line for, it only intersects once. Now the reason I need to make that so clear is say we go back to this function that I've drawn on the left, so I'll leave this up for about 5 more seconds, the one with the orange line. So if I go back to my other graph that I'm actually working with, so what I'm saying is that line is a tangent line, that green forest green line is a tangent line, so it only intersects the function at x equals 2. So if I want to talk about the slope of that line, well, to find a slope I need 2 points, right? We only know how to find the slope if we have some x2, y2, and x1, y1. So we need 2 points to be able to find the slope. But I only know one of them. I only know that it intersects at 2, so I can't really, at this point in time, we will find something out later that lets us do it later. But at this point in time, we have absolutely nothing to tell us how to find the slope of that line because we don't have a second point to work with. So the point, what I'm trying to get at, is what we're going to do is say I were to take, 2 points, one at 1 and one at 3. And I draw the line between them. That's a very, very bad line, but just pretend it's not horrendous. Now, if I talk about what this line represents, this would be the average rate of change between, between x equals 1 and x equals 3 is going to be the slope of this line. Pen, hello. Slope of this line. But so we could actually find the slope of that line if we knew what this function was, because we have 2 points instead of just 1. But notice that that slope of that line doesn't really look like the slope of the green line at all, right? But what we're going to be doing, different color purple, is we're essentially going to be bringing those points closer and closer to the point we actually care about. So say I take, 1.5 and 2.5 and draw the line between them. So we'd have another average rate of change here between x equals 1.5 and 2.5 would represent the slope of this line. Now the slope of that purple line that I just drew is, while not exactly the same thing as the slope of the green line, it's much closer than the slope of the red line. So as I make these 2 points get closer and closer to x equals 2, the better the approximation is going to be. So essentially what we're going to be doing is we're going to be estimating, so let me kind of write this off to the side here. So to estimate the instantaneous rate of change, which I'm going to abbreviate if you'll let me. So to estimate the instantaneous rate of change, we're going to find the average rate of change for a small interval, which I've kind of already said, but I'm just trying to like hammer this into your brain like 5 different ways so that it sticks. But this is the idea of what we're doing is we want to estimate, we don't want to estimate, we want to know the slope of these tangent lines but we can't find the slope of a line with just 1 point. So we need to do the best we can, which would be to find the average rate of change using 2 points instead of just 1. One other thing that I need to define in case I say it, it's not used as often as tangent line, but there's a word secant line as well. And this is just a line between 2 points on a function. Pick any 2 points on a function, draw a line between them, you got a secant line. So that red and purple line in the thing that I just drew are both secant lines. You're going to hear me say tangent line way more than secant line, but just in case secant line slips out of my mouth, you kind of know what that is. So we haven't really done a full yet, so let's get around to one of those. So essentially all we've done is we've built up this idea of finding this new thing called the instantaneous rate of change, but the best we can do is to estimate it with an average rate of change. So I also want you to recognize while we're using average rates of change, they're not the same thing. It's just that we can't find exactly the instantaneous rate of change yet, so we need to have the best we can, which includes an average rate of change. Hopefully that made sense. Anyway, I'll leave this up for 5 more seconds before I scroll up to do the examples that I went past. And okie dokie. So say we have the quantity in milligrams of a drug in the blood in time t in minutes is given by the equation 25 0.8 to the t. Estimate the rate of change. So they dropped the word instantaneous, but it's the same thing. So estimate the rate of change of the quantity at t equals 3 and interpret your answer. So again, we can't find the rate of change exactly at this point in time. A few weeks from now we will, but we can't do it yet. So what we have to do is we have to estimate it with the average rate of change. So what we're going to do is we're going to find the average rate of change between, what is happening with my pen? Between t equals 3, not x. T equals 3 and something very close to 3. Because again, we're using this idea of the closer we get to the point we care about, kind of that diagram I just drew, the closer we got, the better the estimate was. So we're essentially, since we have an equation, when you have an actual equation, this is the one where you're going to be able to get a really, really good estimate because we can choose whatever values we want. It's not like when we were given a table, because when you have a table, and we'll see another table example in a second, when you're given a table, you're kind of stuck. But when you have an equation, you can choose whatever the heck you want. So a couple of things. Well, no, let me do this first. So what I'm going to use is I'm going to use t equals 3 and 3.001. When I say very close to 3, I mean it. Now, kind of side note, you could also use 3.01. You could even go the other way and use 2.999 or 2.99. I would not use something like 3.1 or 2.9. I know in some contexts, 3.1 would be pretty close to 3, but in this context, it's actually farther away than we want it to be. So we kind of want to get as close as possible. Now, we could, of course, get closer. We could do something ridiculous like 3.000000001, but, you know, you got to stop the insanity somewhere. So I usually go with, you know, just adding on a 0.001. A note about Wiley, I think Wiley does this, is sometimes they'll say something like, let H be 0.001 or 0.1 or whatever. I think they sometimes also might say change in X. If you see something like that, they're essentially telling you what to tack on the end to the point you care about. So they're essentially forcing you to use 3.001 or maybe even 3.1 or something like that. So if they don't specify, you do get to choose. I would always suggest just choosing 0.001. But if they do state it in some way like this, then you're forced to use a certain number. Anyway, still haven't actually calculated yet. So you've got the two values that you're going to use. We're going to use these two. So you're going to find the average rate of change using those two values. So we essentially want to find the Q value at 3.001 and then the Q value at 3, and then subtract 3.001 minus 3. So we had our function, so let me just do one other intermediate step so people know where I'm pulling my numbers from. So that function was given to us. And now I just got to find my values. So I don't have my answers in front of my face, so I got to calculate these really quick. To the 3.001. So one more thing about these. Take as many decimal places as possible. So this comes out to be 12.797114. It technically has 2 more decimal places in the calculator, but you know, I've taken 6. 6 is usually good enough. You want to take at least 4, but usually you want to take something more like 6 of them. And then I calculate 25 times 0.8 to the third, I get 12.8. Especially with Wiley, take as many decimal places as you can as you're doing it, or else you might end up with the wrong answer. Well, quote unquote wrong answer. Wrong answer for Wiley. So 12.797114 minus 12.8. I'm running out of space, especially because I was supposed to interpret. Whoopsies. So we get negative 2.886. I'm going to kind of drop down here because I was supposed to interpret it, so I'll interpret it in there. Any questions, concerns about how I found that number? 12.8? That came from, there's a little thing in the way and I can't reach my, this 12.8 came from the 25 0.8 to the third. What did that buzz again for? Is that just registering? Okay, yeah. So yeah, the 25 times 0.8 to the third is what gave me the 12.8. And the 12.797114 came from the other one, the 3.0011. 11. Anyway, so let's declutter that a little bit. So I've got this value here. Now this is still a slope. So if I wanted to talk about the units of this, so let me move this over just the tiniest bit so I can write the units next to it. The units of this are going to be the units of essentially the Q values over the units of the T values. So we would have milligrams per minute. Now, since this is a slope and I want to interpret it, we're going to interpret it like we interpreted our slopes. So remember, when interpreting slopes, you kind of have your two choices. You can either phrase it as a rate, or you can phrase it as like increasing by 1 in the X direction, increases by how many in the Y direction. I'm going to go ahead and write down the rate way. And for that, remember, you always have to tell them where to start. So we would say after 3 minutes, you kind of always have to remind them the number you actually cared about. So we were finding the instantaneous rate of change at t equals 3. So after 3 minutes, the amount of the drug in the body is decreasing because the slope was negative by 2.886 milligrams per minute. Sorry, I ran out of space for interpreting that. Questions, concerns on the interpretation piece? Okay. So next definition is the derivative. So the derivative of f at a, which is written, this would be read as f prime of a. So the derivative of f at a is defined to be the instantaneous rate of change of f at a. So the instantaneous rate of change and the derivative are equivalent. So they mean the exact same thing. They are used interchangeably, although moving forward, in chapter 2, we'll say instantaneous rate of change a decent amount of the time, but after chapter 2, we pretty much always refer to it as the derivative. So they are the same thing, but it's just two words that mean the same thing. But the derivative essentially now gives us this new notation as well. So say I wanted to estimate f prime of 2 if f of x equals x cubed. So that's asking me to estimate the instantaneous rate of change at x equals 2 for the function x cubed. So this is the exact same idea that we just did. We want to take 2 and something really close to 2. So say I said let x be 2 and 2.001. Again, personally, I usually default to 2.001 or adding 0.001 to the point I care about. So if I were to do that, then we need to do the average rate of change between those two values. So if I plug 2.001 into x cubed, so let me just write out the intermediate step, I guess. 2.001 cubed minus 2 cubed. And I take as many decimal places as I can, at least 4, but I'm going to go ahead and take 6 of them again. So I plugged 2.001 into the function, and then I plugged 2 into the function. Once my screen catches up to me, there we go. So we're going to have 0.012006 over 0.001. I was hoping to not run out of space in that direction so I could do something below this. 12.006. Nope. I'll just, you know what? I'll rewrite it. It's okay. Boink. No. So did we just have 12.0? Oh my god. No, it was 8.01200. Why are you being so stupid, little pen? 006. Oh, and my 2 got deleted now. I should have just let it be. Oh my god. What is happening? The point is that the answer for that one was, oh my god. 12.006. Goodness gracious. Now, if you know derivatives, and again, you're not expected to, so when I say that, I'm just literally talking to the people who might already know where we're going with this. if you know derivatives, you know that we'll eventually be able to do this in about 2 seconds instead of like 30. And that the answer should be exactly 12, which is another reason why I actually take as many decimal places as I can, because I actually don't want it to be exactly equal to 12, because that's not technically what we're getting here. But also, I want to do something else. So that is a perfectly acceptable answer for this question, 12.006. Just for giggles, what if I had essentially gone the other way and I had instead subtracted 0.001? Oh my god. Suddenly my pen is acting up. I'm going to go through this one slightly faster, but if you need me to talk about any of the pieces, just let me know. So 1.99 cubed would be 7.988006 approximately. This one would turn out to be 11.994. The reason I wanted to do that is because, note, those aren't the same answer. 12.006 does not equal 11.994. This would also be a completely acceptable answer to this question. So depending on not only what number you kind of tack on to the end, but it also depends on kind of which direction you go in. If it's not specified, do whatever floats your boat. And if you think it's Wiley being weird, let me know. But Wiley should either specify or have a large enough tolerance to handle it. But as always, if Wiley's being weird, just let me know. But either of those two are perfectly fine, whichever one makes you feel better. David, what up?
Okay. So what you did on example 3, now to go further, it doesn't matter how you do it. Like I wouldn't say for just for example 3, but I would say before the definition of 3 on example 2. Okay, what you did on example 2, it doesn't matter how you do it. Okay, say like 3.001 minus 3, or you can say like 3 minus 2.999.
Exactly. So if it's not specified, you kind of get to choose. If it is specified, sometimes they'll say let H be 001 and find the estimate on the right, if you will. If they say something like that, then they're telling you to essentially take 3 and 3.001. If they say something, maybe they specify in terms of the left, then you would need 3 and 2.999. I'm talking example 2 lingo for some reason. So if they don't specify, you get to choose, but sometimes they will specify to kind of force you to do one specific way. But if they don't, then you can do it however you like.
Oh, okay, because even if you do either way, it won't be the same answer, but it could be somewhat closer, right? Like,
yeah, you're gonna get really, really similar answers, like 11.994 and 12.006 that we just found. Those are obnoxiously close to each other. They're both really close to 12. So you'll get, kind of in the same ballpark, but they might not be exactly the same answer, which is fine.
okay, that'll work. Thanks.
Yeah. All right, any more questions about how we did those before I move on to a slightly different idea? Same topic, but just slightly different idea. Okay. Alrighty, so the next idea, I'm going to be pulling on this idea that all of the things we've been talking about, average rate of change, and now this new instantaneous rate of change, are all slopes. Slope, 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 slope. They're all slopes. Okay, now I can do the next one that I've said slope about 5 times. All right. So say we have this graph of x squared. Now I've swallowed wrong and can't breathe. You know you've got problems when you can't even breathe, right? All right, we've got the graph of x squared, and we want to determine whether the following values are probably positive, probably negative, or probably approximately 0. So these are all derivative values. So remember, the derivative is equivalent to the instantaneous rate of change, and the instantaneous rate of change is a slope, and specifically the slope of this idea of this tangent line thing. So let me get a couple different colors floating around here. I'll do the first one in red. So if I want to look at f prime of 1, let me go up to x equals 1 and go up to the function at 1. Now, drawing tangent lines is hard. They're even rough for me, and I don't say that in a condescending way. I just mean I've been doing calculus for like 5 million bajillion years, it seems, and I still can't really draw tangent lines very well. The best advice I can give for drawing tangent lines is plot the point that you actually care about, and then imagine kind of plotting a point kind of directly next to it. Oh, and then make your screen accidentally zoom in. And once you do that, you kind of have those 2 points to kind of focus on, and you just draw the line between those two. So here's what our tangent line at x equals 1 would approximately look like. And so since we're looking at slopes, is the slope of that positive, negative, or approximately 0? Since that's an increasing line, an increasing function, this value would be positive. I don't know what it is. I don't know the number. But I know that it's going to turn out to be positive because the slope of that tangent line is positive. David, is that a new question, or did you just not put your hand down? I wasn't paying attention.
Oh, my bad. I forgot to do it. My bad.
You're fine. I was just making sure.
It's cool.
So, one, different color. So at -1, let me go up to the function at -1, draw a tangent line. So let me plot a point like kind of right next to it to try to figure out the direction my tangent line's kind of taking, and then it's going to erase itself. Fun times. So again, the derivative is a slope value. So is the slope of that function going to be positive, negative, or approximately 0? That line is decreasing, so it's going to be negative. What is happening? Negative. And that screen is obnoxiously frozen. Come on. You can do it. There we go. Negative. If I want to do f prime of 2, lime green going on. Maybe I should do a darker green in case people are colorblind. They can hopefully at least see the darker color. F of 2 is up here. Up here. Up. Draw the circle. Oh my god. F of 2. Thank you. Goodness gracious. Plot a point kind of directly next to it to figure out the direction that your tangent line is going to go in. Draw your tangent line to the best of your ability. So when I'm plotting these second points, that's not really an official point by any means. It's just a point that's allowing me to draw it better. Because remember, the tangent line only intersects the graph at that one singular point. So me saying plot a point directly next to it on the function is not really official. I want to be very clear about that. It's just kind of a tip to help you draw it. Is the slope of that line positive, negative, or approximately 0? And it's positive. And then what about at 0? At 0, we're kind of at the bottom of this parabola. If I draw a point directly next to it just to help me draw my tangent line, we're pretty much just going to have a straight horizontal line. So is the slope of that line approximately positive, negative, or approximately 0? That one's going to be our only one that we can say is approximately 0. It's going to be exactly 0, but we're just going to say approximately 0 because we're not entirely sure yet. So if you ever want to look at kind of the sign of a derivative, you can imagine the tangent line and then figure out whether the tangent line has a positive, negative, or approximately 0 slope. Questions, concerns on that? Before I do a slightly similar example. Okay. Same idea, different graph, and slightly different questions. Why is this? Can I make this little thing go away? Oh, I made it go away. Okay, cool. So f prime of 1. So again, we have a derivative value here, so an instantaneous rate of change, so a slope of a tangent line. So if I go up to f of 1, plot something directly next to it just so that I can help draw my line, not officially on the line, but just help me get the idea of what it'll look like. So here, we were not only asked to find are they positive, negative, or approximately 0, but we are asked to illustrate them. So I should be kind of clear that it's the slope of this line. It's not like the line itself that represents the value, it's the slope of it. But since the slope of that line would be positive, this f prime of 1, whatever it is going to be some positive number. I don't know what the number is, but I know it'll be positive. And now we get into the tiniest bit of a different piece here, because now we have something that isn't presented as a derivative value. It's presented as f of 3 minus f of 1 all over 3 minus 1. But that looks a heck of a lot like an average rate of change setup. F of b minus f of a all over b minus a. So this would be representing an average rate of change, and specifically the average rate of change between 3 and 1. Well, what does that actually look like on the graph? Well, remember that the average rate of change is also a slope, but it's the slope of the line between those 2 points. So if I draw the line between 1 and 3, the slope of this line will be this value, because that value is finding me an average rate of change. Now I'm going to say this one's approximately 0. It does look like it's increasing the tiniest bit, but it also looks pretty horizontal, so let's say it's approximately 0. I also think I drew that a little poorly. If I had drawn the line kind of down the tiniest bit because it goes through this point a little too high. But anyway, so let's say that one's approximately 0. And then I've got this last one. Now this one's a bit harder to see. This one, it's not talking about a slope because it doesn't have the right setup to be a slope. It doesn't have a, change in y over change in x. It's just essentially taking 2 values and subtracting them from each other. Well, let me find where those 2 values are on this graph. Well, here's f of 4, and here's f of 2. So if I kind of think about kind of the distances between these two, this value of f of 4 minus f of 2 is going to be essentially this distance here. Maybe I'll just say distance. Now this one takes a bit more thought as to whether it's positive, negative, or 0. F of 4 is the smaller value because it's lower on the function. And f of 2 is the larger value. If you take a smaller number minus a larger number, it's going to result in a negative. I don't know what the number is, but I know it's negative. Questions, concerns on that one? This is taking a little longer than I expected. Oh, and wait, we end at 4:05, not 4:15. What the heck am I thinking about? Ooh, Lord. That's not great. Oh, well. Anyway, last one, and then maybe I can talk about 2-2 the tiniest bit. Maybe I'll just breeze through it a little bit and come back to it on Thursday. Anyway, following table notes the total farm land in millions of acres. Use it to answer the following questions. What is the average rate of change between 1997 and 2012? So 1997, 2012. So here we're just the average rate of change, excuse me, so what we did back in chapter 1. So we have our 932 minus 915, 1997 minus 2012. So 932 minus 915 is 17. And then over negative 15. The 932 and the 915 are talking about farmland, which was in millions of acres. So this will be in million acres per year. And then kind of the piece of, actually the new piece for 2.1 is we're asked to estimate f prime of 2007 and interpret our answer. So now we care about 2007, and ideally we would be able to look at something obnoxiously close to 2007, but we don't have that here. We don't have an actual equation. We can't figure out what, you know, f of 2007.001 is. So when we have a table and we're kind of locked into the values we use, this is where we're kind of going to go back to the idea that we talked about in kind of that introductory example. We're going to take the average rate of change kind of on both sides, and then we're going to average the two. So we're going to find the average rate of change for 2002 to 2007. Then we'll find the average rate of change for 2007 to 2012. Then we'll average the two. So it's unfortunate that average rate of change and just the generic average both say average, but that's what we'll do. And then we'll interpret at the end. Interpret, kind of setting up our hoopla here. So if I want the average rate of change between 2002 and 2007, I'm looking at 938 minus 922 over 2002 minus 2007. I trust and believe we could type that into a calculator, so I'm going to go through the calculations somewhat quickly, but of course, always stop me if you need to. 16 over 5 would reduce to negative 3.2. Once it catches up to me. That one screen is lagging a lot. There we go. And then the average rate of change between 2007 and 2012, we'd have, again, personal preference, I just like putting the larger y value first. So 922 over 915, so 2007, oh my goodness, minus 2012 would give us 7 over negative 5, which reduces to negative 1.4. We're going to average those two numbers together. So remember, when you average numbers, you add up all the numbers and then divide by the the number of numbers you're adding up. So we'd get negative 2.3 as our estimate for f prime of 2007. So since we couldn't get obnoxiously close to 2007, we kind of did the best we could. And the best we could in this case is to take the average rate of change on both sides and then average the two. If I wanted to interpret this, again, this is a slope. So you always tell them where you're starting. So we're starting in 2007 and we're talking about the change in farmland. So we'd say in 2007, the amount of farmland is decreasing by 2.3 million acres per year. Questions, concerns on how I found that? Okay, for our last 9 minutes of class, I do want to introduce 2-2, because really this took longer than I thought it should, but that's okay. So I want to try to introduce the idea of 2-2 so that we can definitely get through 2-2 and on to 2-3 on Thursday. 2-2 is a pretty short section. So I want to kind of get the idea out for it. I'll say this really quick though. For your quiz on Thursday, it's essentially going to cover just 2-1. So you might have something in a table where you need to find the instantaneous rate of change. You might be given an actual function. You need to find the instantaneous rate of change. It's going to be finding the instantaneous rate of change in kind of these 2 ways we kind of saw today, either using a number obnoxiously close, or if you're given a table, taking both sides and averaging the 2. And I'll type that in chat at the end of class once I talk about 2-2 a little bit. So 2-2. Do I have 2-2 notes up already? They're over here. Hurry up, Aaron. So 2-2 is done a little differently because usually I like to do this kind of activity, but then I realized I was going to try to do it anyway with you guys, like you would just do it on your own, but then I realized that that would probably go over very terribly. So I've kind of been walking everyone through it kind of in a way. So since I don't have a lot of time, I'm going to breeze through the idea of it and I'll talk about it a bit more again I'll kind of come back to it on Thursday. But kind of the idea behind it is, so this thing that you have in front of your face, it's got this line and that's going to be the tangent line. So we talked about tangent lines. So if I kind of move this around, this is going to give me the tangent line of the function at any of these points. And it's nice because it actually gives me the exact one. I don't have to try to draw it like a dork. And essentially what you can do is you could actually then find the actual slopes of these lines. So say like for this one, and I'll come back to this on Thursday, if we wanted to find the slope of this line, we would start at this point here, we would move over 1. And if you kind of follow my cursor, we'd have to go up 1, 2, 3, 4, 5, about 5.5 before we hit the line again. So I could essentially say that the slope of this line is 5.5. So if I essentially go and I do that for all of these points, and I'll do that in more detail on Thursday, but if I go and I do that for all of these points, I find all of these kind of slopes for these tangent lines. What we're going to be able to do is, and again, I'll come back, I'm going to like briefly talk about it and then we'll come back to it in more generality, not generality, in more detail on Thursday. So this is the graph that I just left. And so we were, Desmos was helping us out by actually drawing these tangent lines for us. And essentially what we can do is we can find the slopes of all of those tangent lines. And if we find the slopes of all the tangent lines, which we'll go back and do fully next time, but if I just like fill them out super duper quick, just for the sake of presenting the idea behind this. If we were to find all of the slopes of those tangent lines, we could essentially then go and graph our own function using these as points. So essentially what we can do is we can find a bunch of slopes and then we can plot our own function. So say I took those points, stop being stupid, there we go. We took all of these points, so I was actually treating these as coordinate points. So I'm treating this as 2, 5.5 and -1, 2. So sorry, -2. 0, -1, 1, -2. So I'm essentially taking the x values and the slopes of their tangent lines and creating new coordinate points from them. If I were to plot these guys, and I know I'm going through this super duper quick, again, gonna come back to it. Just want to kind of get it in your brain as a thing that's gonna happen. -1, 2, 0, -1, 1, -2, 2, -2.5, 3, -1.5, 4, 1, and then 5 I kind of forgot to plot on here. If I connect these points together, that looks like a parabola. So this looks like a parabola. And parabolas are functions. So what I've essentially done is I've taken a bunch of slopes, a bunch of instantaneous rates of change, a bunch of derivative values, and I've found a function that actually gives me those values. Well, I don't know the actual equation, but I could, or someone could, find the actual equation to that parabola, and we'd be able to find the slope at any point. So the point of 2, is that we're essentially going to look into the fact that the derivative values itself gives us a new function. And what we're going to be doing, so we'll go through this a tiny bit, we'll kind of review it really quickly on Thursday, and then we'll move forward, is what we're going to be doing is we have kind of this relationship between the original function and what we're now going to have is this derivative graph. And what we're going to be doing is we're going to be essentially looking at original functions and then being able to determine out of some options which one of them is a derivative graph. So the basis of 2 is this idea that we have a derivative function that we can kind of get from the original function by finding a bunch of slopes. And there's going to be this relationship between the two. So we didn't really get anywhere with that, that very much, but at least to kind of give you an idea of where we're going with that. So I know the very beginning I said we were going to finish 3-3 by Thursday. We will definitely get to 3-3. We just might not finish it by Thursday, and I will apologize in advance for that if that happens. But we will finish 2-2. 2-2 isn't that long, so we'll finish 2-2, start 2-3 on Thursday. And if there's a tiny bit of 2-3 we have to finish on Tuesday, it'll be unfortunate, but it'll be a thing. So let me reiterate what your quiz is in chat. So this is going to be purely on the instantaneous rate of change, which is from 2.1, what we just covered. And there's kind of your two options. There's when you're given a function and you use something like 2 and 2.001. And then there's given a table, and that's where you kind of have to use your kind of find average rate of change on both sides and average. So I just typed that out in chat in case you want to find it later or just take it down now. That's what your quiz on Thursday will be on. Did it send? I think it's still trying to send, so you might need to give it a second. But that's that. Again, I will get your exams out to you as soon as I can. Yes, this Thursday, instantaneous rate of change quiz. So we'll go through some examples in our warm-up and then continue with 2-2. Is there a curve for the exam? I usually don't curve my exams, and that's usually because they don't usually need one. So my two other sections, I finished first because, well, they were also 50-minute exams, so they were slightly shorter. Both of those, the class averages were like C pluses, which you might not think sounds good, but that's usually where we want it to fall. We want the average to be at a C. But there were also lots of B's and A's. They were a little hot and cold, of course. But for the most part, my exams don't usually need curves. I'm very generous with partial credit. So no, there's most likely not going to be a curve. All right, so we are officially 1 minute over. So if you need to leave, feel free. If you have any questions about anything, feel free to stick around for a little bit. Otherwise, have a great day. I'll see you on Thursday. We'll stop the recording. Thank you.